Section 1.4 is calculating limits. So in the previous section, we introduced the idea of a limit, at least the intuitive definition, and left aside the precise definition for another time. But now we're going to talk about how to calculate limits of functions. And one of the main tools we actually have for that is the set of limit laws. So these are really a set of theorems that are proved in the book or otherwise that allow us to calculate limits of functions or combinations of functions like f of x plus g of x or f of x minus g of x and so on down the line. So let's have a look at these limit laws in further detail. So we let c be a constant. In other words, that's some real number. It's just standing in place for any real number. And we have functions f of x and g of x that have limits as x approaches a, f of x approaches L, and the limit as x approaches a of g of x is equal to m. So two different limits, L and m. So now these two limits exist, right? Since they are equal to L and m, some real numbers. So if I have the limit of the sum of these functions as x approaches a, notice it's the same x value that x is approaching, then the limit of the sum of these two functions is equal to the sum of the limits. Another way to write this actually is to write it in limit notation. We can split up the limit over the sum. Limit of f plus g is equal to the limit of f plus the limit of g, moving from the left-hand side to the right-hand side. So this is the additive property of limits, and this holds true for subtraction as well. The difference between f and g is L minus m, and the limit as x approaches a. Now for that constant c, so some real number times our function f of x. Remember, f of x's limit is L as x approaches a. So the limit of as x approaches a of c times f of x is equal to c times the limit of f of x. Well, that's L. Or another way to write that, or the way I just said it, is like this. And the limit of the product of the functions is L times m. The limit of the quotient of the functions is L over m, provided that the limit as x approaches a of g of x is not 0, right? We want to avoid division by 0. It would be undefined if g of x approaches 0 as x approaches a, or if its limit is 0 as x approaches a. So that's one caveat there. And there are a few more limit laws that kind of are a little bit adjacent to that step, but not quite in that initial group of limit laws. If we take f of x to some positive integer power n and take its limit as x goes to a, well, the limit that results is the limiting value of f raised to the nth power. It's more or less what we would assume or hope for. So the limit of a constant function, right? Remember, c was just some constant. It's not a function of x. It's just some real number. So say if this was 2, then that value would be 2 on the other side, right? We move x, but there's no x in our expression here to change, so our expression just comes out as a c. That's a useful thing to remember for limits. Similarly, the limit as x approaches a of x is just a, right? This is the identity function's limit, right? So as x approaches a, well, its limit is a. If x to the n, we get a to the n. So that's nice, similar to what we saw up here. And then the nth root of x, we get the nth root of a, where n is some positive integer. And if and if n is even, also. A needs to be greater than 0 if n is even. So if n is odd, it's fine. We don't have to worry about the values of a at all. Because odd roots of negative numbers exist that are negative. Even roots of negative numbers are imaginary numbers, and we don't allow those in the course. So let's see. Limit as x approaches a, the nth root of f of x is equal to the nth root of L. Again, where n is a positive integer, and if n is even, then f of x has to be greater than 0 near a. Okay, so a lot of different rules. We'll be able to apply those in a bunch of different places. So when we start to use these rules, at least in this section, and maybe a couple sections moving into the future from here, we want to be able to identify which rule we use in every step just for the practice of the whole thing, right? So here I'm taking the limit as u approaches -2 of the square root of u to the fourth plus 3u plus 6. So I want to see what this function's limit is as u approaches -2. So I'll use my limit laws, and off to the right, I'm going to cite every time I actually use one of these limit laws. So to make the move from here to here, I'm actually using number 11, limit law 11. So by 11, we're able to say this. We're able to say that rather than taking the limit as u approaches -2 of the square root, we can move the limit inside the square root. And that's essentially what this is telling me. If this function inside here, in other words, this function, has a limit, well then the limit of its square root as u approaches -2 is going to be the square root of the limit L that this thing approaches. So in other words, 11 lets us make this move. And now the limit is closer to these terms, the interior terms of that radical, the radicand terms. Now the next thing we can do is this. This is the limit of a sum of terms. So now I can use my rule number 1, limit law number 1, and take the limit of each of these three terms and add them up. So I can do all these individually. So that's nice to know and be able to use. And the next thing we see here is that -2, well, we're looking at this limit, u to the fourth. This is a power function limit. The limit as x goes to a of x to the n. Now that in this case, it's u going to -2 and it's u to the fourth. Well, this is now -2 to the fourth, right? We can plug that in as we have in limit law number 9. Similarly, we have u approaching -2, 3u. We're taking that limit as well. And what we see here is we can factor the constant 3 out. This is by limit law. I think that's actually limit law number 3, even though it says limit law 2. This is where we can factor a constant out of our limit to have 3 times the limit of u. So that should be limit law number 3 down here for this one. And lastly, we're taking the limit of 6 as u approaches -2. Well, this is a constant function. This is c is equal to 6 in this case, some constant, and this is using limit law number 7 up here. So the limit of 6 as u approaches -2 is simply 6. So that one evaluates pretty easily. Constants are nice like that. Now the last thing we need to do is evaluate this limit. And well, this is the identity function, u, right? So we use limit law number 8, and we get that as u approaches -2, well, this limit is equal to -2. And now we just simplify everything underneath this radical. We have 16 minus 6 plus 6, we end up with the square root of 16, and that comes out to 4. So all along the way, I'm able to identify each step that I use, each limit law that I employ to simplify my expression until I get to the very bottom and have evaluated all the limits. So this is evaluating the limit, right? Turning this limit expression into a value. Now, we won't always have to do that, right? Later in the course, we'll be a little bit more fluent with limits, and we'll probably relax these exercises of naming all of the steps. But for now, it's good to do that because you'll learn all the different limit laws that are available. And when the expressions are harder to deal with, it's nice to know which limit laws are at your disposal. So, a direct substitution property. This is probably what we thought of the first time we saw a limit back in section 1.3. Why don't we just plug the value directly in? Well, we saw other functions where that wasn't actually feasible. Well, it turns out a group of functions, or two groups of functions, are polynomials and rational functions. So if f is a polynomial or a rational function, then, and a is in the domain of f, then if we're taking the limit as x approaches a of f of x, well, that limit is just f of a. And this is actually by continuity, and we'll see that in section 1.5, but we're getting this sort of a little bit ahead of time in this section. It's kind of a sneak preview of that. So we have to evaluate each of these limits given in this example. Now we have the limit as x approaches 3 of x squared minus 4 over x minus 2. So it'll help us to be able to classify this function, right? If I look at this, I realize x squared minus 4 is a polynomial. X minus 2 is also a polynomial. They're in ratio to each other. So x squared minus 4 over x minus 2 is a rational function. Since it's a rational function, I can now use my rule above and check, is 3 in the domain of this function? Well, the only thing we have to worry about for a rational function is to make sure that the value that we're attempting to plug in does not cause a 0 in the denominator. It doesn't in this case. So it looks like 3 is in the domain of this rational function. So now I can take 3 squared minus 4, just plugging 3 in exactly as this rule tells me. I can just plug these things in and work from there. So in the numerator, I've got 9 minus 4, which is a 5, over 3 minus 2, which is 1. And then our result is a 5. Okay, and again, we've noted that the domain of this function is everything except for positive 2, everything except for the value that makes the denominator 0. Okay, as x approaches 2, taking the limit of x squared minus 4 over x minus 2. Okay, so, well, in this case, we'd think, well, I'll try direct substitution, but the problem is, when I do that, we realize that 2 is not actually in the domain of this function. So we're kind of out of luck here, right? So we can't just go plugging it in. We'll get a 0 in the denominator. But if we think about this a little more closely and remember a little bit of algebra, we'll recall that this function actually factors, this quadratic factors as a difference of squares. X minus 2 times x plus 2, that's the 2 being the square root of 4 and x being the square root of x squared. And so if we look at this expression, this rational function, we realize that we have factor x minus 2 times x plus 2 for our numerator. And there's a common factor between the numerator and the denominator, and that's that x minus 2. So in this case, we get kind of lucky, and the x minus 2 in the denominator cancels with the term in the numerator, and we're left with x plus 2. So we can rewrite this function as this. It's the limit as x approaches 2 of x plus 2, and that's what we see down below after this cancellation. This work over here is just off to the side just to show the algebra if we weren't comfortable carrying on the limit notation while doing that. Now, this is a polynomial, so we're allowed by our theorem above to use our direct substitution. We can now plug in 2 for x to evaluate this limit, and we have 2 plus 2, and our limit is 4 in this case. So this one took a simplification step, but we're still eligible to use that direct substitution rule. So if these two if the denominator term did not cancel with the numerator term, well, then we'd have to do some more work, and we're going to see that in other sections, how to handle those types of cases. So this is sort of a special rigged case for these problems in section 1.4. Okay, next up, let's generalize this a bit more, right? So if we just used a result, more or less, or sort of an implicit result, or tacitly used a result in that previous example. If we have two functions f and g that are equal to each other whenever x is not a, so they're equal everywhere to each other except for the x value of a, so these two just miss each other at a, well then the limit as x goes to a of f of x is equal to the limit as x goes to a of g of x, provided that that limit exists. So really what we know about that last function is the following. This is a little bit interesting here. We know that 2 is not actually in the definition of this function. So if we consider this to be f of x, we're able to cancel it and come to f of x being equal to this function. But by its original definition, we know that f of x does not have 2 in its domain. But we arrived at a function g of x that's equal to this function everywhere, except for when x is 2. So we could take g of x's limit here, and then it's equal to f of x's limit as x goes to 2 as well. So that's how we know that this one's equal to that. So that's maybe the theoretical background. If that doesn't make as much sense, then that's okay for now. Maybe it'll make sense later as you start to practice these problems. Okay, so now let's jump into a more general example. So here's another one where we have this isn't quite a rational function because the numerator is not a polynomial, right? It's got a square root in there, and that makes it not polynomial. But it's a rational expression, and we think about this, we say h is going to approach 0. We don't have a rational function or a polynomial, so we can't really do much here in terms of just direct substitution. So we have to kind of work our way, in some more clever way. What we should notice here, we have the square root of something plus or minus something else. Whenever we have that, we might want to simplify it. We realize that this thing has a conjugate, right? I take the minus sign in between those two terms and I change it to a plus sign. Then I'm going to take, this is called the conjugate of this expression, right? And then I'm going to make a form of 1, right? I'm going to write that term down and then divide it by itself so that all of this is equal to 1. We see off to the side, right? This thing, well, at least this part's equal to 1. So it doesn't change my overall expression. And when I multiply by this conjugate, what I should get is this term squared minus this term squared. And the middle term should cancel because -2 times that radical plus this radical times +2 is going to add to 0. So the inner terms add to 0. So I have this squared plus this, or minus this squared. The middle terms have added to 0 here. And the bottom just kind of comes along for the ride, right? H is multiplied by this conjugate term, and we'll deal with that in a moment. Hopefully things have gotten better after this step. If not, we have to go back to the drawing board. So here we are with 4h minus 4, that's this expression here, over the denominator that we haven't changed yet. And then we realize that 4 minus 4 adds to 0. So this is a 0, and we have just an h in the numerator. And then there's an h in the denominator, so those two h's cancel. And we have 1 over 4, root 4 plus h plus 2. Okay, so now we could start to think about using limit laws, right? And maybe the first limit law we use here would have been the quotient limit law, to take the limit of this constant 1 over the limit of this function, to get 1 over, and then we do the sum limit law to access both of these terms. The limit of 2 is just 2. And then we use the root limit law to get inside here at 4 plus h, the sum law to get to 4 and h, and then we take, well, the limit of 4 is 4, the limit of h as h goes to 0 is just 0. And maybe that's too many steps for most students, but it's good to be able to identify all of your limit laws. We end up with 1 over root 4 plus 2, so this is a 2 plus 2, and we have 1 over 4 is our final answer. So that one's worth maybe taking a blank sheet, looking away from these notes, pausing the video, and trying to repeat that process on your own, just to see if you can get it. If not, you can use these notes to help you along and keep referring back as needed. Okay, so this is just a reiteration of a rule we saw in the previous section, right? The limit as x approaches a of f of x is equal to L, if and only if its left-hand limit as x approaches a is L, and its right-hand limit as x approaches a is L, right? So the two one-sided limits need to exist and be equal to the same value in order for the two-sided limit or the general limit to exist. Okay, we're going to use this to help us analyze these functions given below. So we're asked to find the limit as x approaches 0 of the absolute value of x. And it's going to be helpful to recall how we've defined the absolute value of x. Remember, it's got this piecewise definition. If x is negative, x is less than 0, then we write down negative x as our absolute value, because again, negative times a negative would be positive. If x is positive, well, then we just write down x, right? Because it'll be positive. So that's how our absolute value function is defined. And let's get to work on it. We're interested in whether or not this thing has a limit as x approaches 0. So we should check when x approaches 0 from the left. Okay, when x approaches 0 from the left, we're plugging in negative numbers. We're on the left-hand side of 0 on the number line, so all of our values are negative. So if we're plugging in values that are negative to x here, then the output is actually negative x. Okay, so now we're taking the limit of negative x as x approaches 0 from the left, evaluating this absolute value. Well, we can take this minus sign and factor it out in front of the limit. That's a constant of -1. So that's our third limit law that lets us do that. And now we're looking at the limit of x as x approaches 0 from the left. Well, I think a table or chart or even the precise definition of a limit, if we really wanted to get carried away, could convince us that this is equal to 0. As we approach 0 from the left, x approaches 0, or the limit of x is 0. Similarly, we work on the right-hand side. We approach 0 from the right, and we get, well, since these are positive values of x, absolute value of x is just x, and the limit as x approaches 0 from the right, similarly, we can argue is equal to 0. Now we see that the left-hand limit and the right-hand limit are both equal to 0, so that, and they both exist, they're both equal to 0, so that means the general limit, the two-sided limit, exists and is equal to 0 as well. So that wasn't very interesting. I think we probably didn't need all those details to do that, but we have to use the same line of thinking to analyze the next function here. This is the limit as x approaches 0 of the absolute value of x over x. It's a newer function, slightly modified with this division by x here. And we'll run the same check. We're going to approach x, we're going to approach 0 from the left with x, and this is the absolute value of x over x. So now I analyze this. All of our x values are negative, so the absolute value of x is going to come out as a negative x. The function tells me to do. Well, there's that negative x divided by x. We end up with negative x over x is just -1. We do all this work inside the limit. When we're ready, we'll try to take the limit. Well, this is a perfect time to take the limit. The limit as x approaches 0 from the left of the constant -1, well, we know our limit law for constants just says the limit of a constant is -1. So there it is. So this limit's -1. The left-hand limit is that. Now the right-hand limit, absolute value x, all our x values are positive. So in the next step, we just write an x here. We have x over x, and you're probably starting to see what happens. We have a 1 in our limit argument. And we're taking the limit as x approaches 0 from the right of the constant 1. Well, that limit from our constant limit law is 1. So very similarly, we calculated the right-hand limit. But notice that the left-hand limit is not equal to the right-hand limit, right? -1 is not equal to 1. So the left-hand limit and right-hand limit might match, but they're not equal. So our two-sided limit, the general limit, does not exist. Okay, so there's it's an interesting fact, kind of an interesting example. So we have to be careful with these things, right? We want to be very meticulous with our steps and make sure that we don't gloss over anything, because it's pretty easy to make a mistake and let our intuition fool us when we work on these types of problems, especially when they're new to us. Okay, so moving along, we've got a comparison theorem and a squeeze theorem for limits, right? So if we have a function f of x and another function g of x, and f is always less than g for x values that are near a, except possibly at the value a, right? We're always excluding that with limits. And the limits of f and g both exist as x approaches a. Well, then we'll have that the limit of f of x as x approaches a is less than or equal to the limit of g of x as x approaches a. So if this function is less than this one for x values near a, then of course f's limit is going to be less than or equal to g's limit as x approaches a, provided those limits exist. Now we can go a little further than that. Say we've got 3 functions, and this is the more useful of the two theorems on this page, the squeeze theorem. That's why it has a name. So we have f of x is less than or equal to g of x is less than or equal to h of x for x values that are near a. Okay, except possibly at a, right? We're allowed to exclude that one, possibly. So if f of x and h of x have the same limit as x approaches a, in other words, they're both equal to L as x approaches a, then the limit of g of x as x approaches a is L also. So off to the right is a pretty nice picture of this. When I look at this, I see here's h of x, here's f of x, and then here's some squiggly function g of x that I've drawn inside. And it's always less than h of x, but greater than f of x, right? We see that this relation is holding up, right? The y values, the output of g of x, right? The red curve is always under h of x's curve, and g of x is always above f of x's curve. So this is holding up, and we see that h of x and f of x have the same limit here at this number a, whatever that number is, and that limit is L, again, whatever that number is. So we see that as x approaches a and g of x, if it's going to obey these inequalities that are part of the conditions of the theorem, well, then it's forced to have the same limit as f and h. This theorem gets used surprisingly often in the class, so we really want to kind of have a decent idea of how it works. So the method for this is not so much finding an answer, right? They ask us to show that this limit as x approaches 0 of this function is equal to 0. Right? We already have the answer in some sense. We're trying to prove it. We're trying to show that this is the case. So all we're really doing is making use of this theorem to show that this must be true. We just have to be clever about this. We think of this as a function g of x, right? And we want to show that it's got this limit of L or 0 in this case. So what we're looking for is we're looking for an f of x that's less than g of x, this function, and we're looking for an h of x that's greater than this g of x, this function here. So we just have to remember a few facts. Remember that the sine function, that's what I'm going to kind of focus on. The sine function is bounded on the left by -1 and on the right by +1. Provided x is not 0, because we have a 1 over x in the argument, it doesn't matter what we plug into this function sine of x here, or sine here, as long as x isn't 0, because that's 1 over x, we're only going to get a value as small as -1 and as large as +1, right? Because the sine function is a waveform, right, that bounces between -1 and 1. Okay, well, that's a good start. Now we've got something that kind of looks like f of x and h of x, but we don't quite have g of x in here. In order to get g of x in here, I just need to turn this function into the 1 in the limit argument. So I just need to multiply by x on all sides of this inequality. Okay, when I do that, I have -x times -1. I have x times sine of 1 over x, and I have x times 1. So now I've got in the middle the original function, and I've got on the outside a lower limit function, or a lower bound function and an upper bound function that I think we can find the limits for quite easily, right? We use the maybe the constant law to factor out a -1 as x approaches 0 of -x, and then that's just the limit of the identity function, right? In other words, this is 0. This one's just the identity function. Limit as x approaches 0 of x, well, that's 0. As x goes to 0, x goes to 0. That's what that limit basically says to us. So the squeeze theorem now is in place. We have that the limit of our function on the left is equal to the limit of our function on the right. And we see that our function in the middle is stuck between those two. So the squeeze theorem automatically implies this result at the bottom, that the limit of the function we're given is actually equal to 0. So this is different than what you've done in a lot of classes leading up to now, right? This is not, we didn't just work to an answer and put a box around it, right? We made an argument to show that something was true. It's kind of like proving the identities that you did in a trigonometry class. It's quite a bit like that, actually, only now we're naming steps and using a theorem. So we provide the conditions of the theorem that make the theorem work, and then we're able to conclude what the theorem concludes by showing that the conditions are met. Okay, so that will take some practice, but that's our starting point for it. So an interesting limit that comes from trigonometry, if there's time, maybe we'll do this live in the class. Maybe a supplementary video is worthwhile, but the textbook does a nice job deriving this limit right here. And this is actually a pretty critical limit to know for later on in this chapter and in the following chapter as well. So sine of x as x, or over x as x goes to 0, that limit is equal to 1. Or I'll read it more correctly. The limit as x approaches 0 of sine x over x equals 1. This is valuable, right? Now they ask us, well, let's make use of this theorem, right? This is a derivation we just haven't seen. We're just going to treat it as a rule that's been given. Okay, we can see in the book where it has been derived. So the limit as x approaches 0 of sine of 3x over 2x. They want us to evaluate this limit, find its value. Well, it seems to behave something like this one, right? Notice this one's troublesome because as x goes to 0 of sine of x, well, that sine of x goes to 0. And then as x goes to 0, x goes to 0. This is a 0 over 0 situation. And, well, we don't really know what that means. It turns out, though, with careful analysis, that it's actually equal to 1. Similarly, we have a problem here. Sine of 3x is sine of 0, and that's 0. 2x, well, when x is 0, this is just a 0 as well. So we might be tempted to say this is undefined, but we have to be pretty careful with this and see if we can line it up to look like this limit. And if so, well, then we're on the right track and have the limit as we need it, have the actual value. So what I'll do is I'll write down my original limit, and I'll think this. Think if I can get this 2 away from this x, right? I can't just use my rule right away because this x and this x don't have any coefficients in front of them. If I could get the same coefficient on the bottom one, then maybe I make a little substitution, and that'll help clarify things. The first thing I'll do is this. I'll just factor this 2 away from this expression. I get a 1/2 times this. So the 2 is now left that x, right? If I were to simplify this, I'd have this expression over here on the left again. Well, since that's a 1/2, I can factor it out of the limit completely. So there it goes. That's my constant rule, provided this limit here exists. So I do that. And now I'm looking at this situation, right? And what I'm thinking is, well, I can't get the 3 out of sine of x. I just can't do that. Right? It's not mathematically correct to do that. Trigonometry doesn't allow us to do that, at least not in that way. So what I think is this. Maybe I can make this x look like this 3x. And I'll do that with a form of 1. 3 over 3. So that way I have a 3 times x in the denominator. But I don't want the 3 times sine 3x in the numerator. So I'll just put it out here in front of the limit. That's fine. I've got a 3 here. I've got a 3 there. Those two 3's would cancel, and we'd have this initial expression here again if we wanted it. So everything's fine. And we're down here at this step. And what we see is that, well, this is a 3x and this is a 3x. If we really wanted to, we could say u equals 3x. And then as x approaches 0, then u approaches 0, or the limit of 3x, or the limit of u is equal to the limit of 3x as x approaches 0, and all that's 0. Anyway, these two match, and that's the important part. Now we can use this limit law here, and we get that this limit as x approaches 0 of this expression is 1. And we have 3/2 as our constant that was left over times this 1, and there's our limit, 3/2. So this is a problem with just a bit of a trick, right? We have to do a couple steps here to sort of manipulate this expression to make sure it's eligible to use the limit that we have above. Well, good. We have one more to do, and then we're done with this section. So evaluate the limit, and here's our limit. It's as theta approaches 0 of cosine theta minus 1 over theta. Now my work is already kind of crowding this thing out, but note that this is our original expression, of course. And then what I did right away was said, well, let's do a quick analysis of it. As theta goes to 0, the denominator is going to 0, right? Ignore this term here for now. As theta goes to 0 up here, well, cosine of 0 is 1, minus 1 is 0. So again, we have a 0 over 0 situation, so we're not quite sure what happens there, right? So we need to get in here and do some nice work with this. So what I think of when I look at this is another conjugate scenario, right? And so sometimes you just try it. So maybe it doesn't work every time, but sometimes you just try multiplying by the conjugate. The conjugate of cosine theta minus 1 is cosine theta plus 1. I just changed the sign in between. Now I multiply this rational expression by this form of 1, right? This ratio on the right here would cancel to 1 if we didn't want it, but we want it because it might change our numerator in a helpful way. So cosine theta times cosine theta is cosine squared theta. Then we have cosine theta times -1 plus +1 times cosine theta. Those middle terms add to 0. Then we're left with -1 times 1 to get -1 here. Good. So cosine squared theta minus 1 is the numerator. We have theta over cosine theta plus 1. Let's let the denominator just come along for the ride for now, and let's focus on the numerator. What can we do with this expression? Well, anytime I see a cosine or sine squared with a 1 floating around next to it, I start to think maybe I can use the Pythagorean identity. If I look down here, remember the Pythagorean identity, which is written on the page, is cosine squared theta plus sine squared theta equals 1. So if I solve for sine squared theta, I get that 1 minus cosine squared theta equals sine squared theta. I think I could turn this into that by factoring a negative out of this expression. And here's where I do that. -1 times +1. So this would be negative if we factored the 1 back in. And then minus cosine squared theta. Well, minus will make it positive cosine squared theta if we factored it back in. So this is the correct step. And moreover, it lands us exactly where we want to be. 1 minus cosine squared theta, right? We've subtracted cosine squared theta from each side. Then we'd see that sine squared theta equals 1 minus cosine squared theta. And that's exactly what goes in here. And this minus sign just kind of tags along. So here we are, and we've got negative sine squared theta over theta times cosine theta plus 1. And let's do, we're still stuck, right? We have a theta down here going to 0, so that's 0. Sine of theta squared is 0 as theta goes to 0, so that's still problematic. But let's see if we can sort of finagle or move these terms around in a way that'll help us out. For one thing, I think one copy of sine theta over theta will give us a limit that we already know, sine theta over theta. So there's a minus sign, that's okay, we'll just move it out in front of the limit. So that's our plan there. The remaining terms, we have another factor of sine theta in the numerator, so that's here. So together these two make up sine squared theta. Our minus sign's still coming along. And the bottom, well, we took a theta to go over here, and then we're multiplying the rest of these terms over here. Cosine theta plus 1 is under that other factor of sine theta. So I know that this one is in a good spot. I know that that's going to go to 1, or actually -1 because of the minus sign. And I'll use a limit law if I need to take care of that. Now this one, sine theta goes to 0 as theta goes to 0. It's a limit that you could have seen in the book before all these, but we're moving a little more quickly in the lecture videos, or you could convince yourself of that otherwise. So let's see. Then we've got cosine theta plus 1 as theta goes to 0. Well, cosine of 0 is 1. 1 plus 1 is 2. So we have a 2 here. Interestingly, though, this sine theta going to 0 as theta goes to 0 sort of really kind of takes care of this whole term. 0 over 2 is just 0. So whatever this was down here, as long as it wasn't 0, we're okay. So let's use a limit law. The limit of this function as theta goes to 0 seems to exist, and so does this one. So we'll split this up as the product. The limit of this product will now be the product of these limits. So, and that's as follows. So now this one, we factor the minus sign out. So it'll be -1 once we evaluate this limit from our previous rule that we saw, our theorem. And this one we just saw by analysis goes to 0. 0 over 2 is just 0. So what we have in total is that this limit is -1 times this limit, which is 0 over 1 plus 1, or 0 over 2, which is just 0. And so that product is 0. Okay, so maybe all these steps, in total we can conclude that this this fact is the case, right? This is a limit as theta goes to 0, cosine theta minus 1 over theta is equal to 0. Now, this seems like a random exercise, but it'll turn out that this one is just as useful as the previous limit that we saw, sine theta over theta, and we're going to need it for sections later on. So this is a tricky problem. I do recommend that you try to practice each of the examples I've done in these videos, in this video, and maybe refer back to the notes or refer back to the video if you get stuck on a step. But learning how to do these derivations would be pretty important. These would be difficult test questions, but nonetheless, understanding how to do this is a really powerful tool here. So in the next section, we'll talk about continuity of functions and why we are able to so easily just think about something like the limit of sine theta as theta goes to 0 is just 0, because sine of 0 is 0. Why we're really allowed to do that will become clear in section 1.5. So hold on, keep practicing these things, learn these limit laws, learn these couple trig laws for limits, and things will start to make sense as you progress.